Alright, in this video we're going to look at another way to determine the magnetic field of a current distribution. We have seen the Biot-Savart law, and we have recognized, I think, that oftentimes the Biot-Savart law is unwieldy. There are certain times where it's actually just impossible to solve the integral, but we saw something a little bit the same with the Coulomb integral, the Coulomb equation, when we had to directly integrate the Coulomb law to determine the electric field. It oftentimes was just frankly hard, and if we had the appropriate symmetry, what we figured out is that Gauss's law offered us an easier route. Amperes law functions similarly for magnetism. Now we got to be careful because there is actually a Gauss's law for magnetism, so I'm not saying that I'm not saying that this is exactly analogous to Gauss's law, but it's going to function for us like Gauss's law functioned for us in electricity. Amperes law says this: the integral, again the closed integral, b dot dl is equal to mu naught I enclosed. Just for the sake of comparison, let me remind you what Gauss's law said. I'll put this over here. Gauss's law said closed integral of E dot dA is equal to Q enclosed over epsilon naught. So you had the electric field evaluated over some surface, where this is the closed integral over some surface. If it's a closed surface, it necessarily bounds a volume, and in that volume could be or could not be some Q. But if there is some Q enclosed in that volume, this says that the electric field is directly proportional to that amount of charge enclosed. Proportionality constant here is 1 over the electric permittivity epsilon naught. All right, now, same thing here. We have a B field, but we don't have a bound volume. It doesn't make a whole lot of sense to talk about a current in a volume. So what we have to do is construct a line, a closed line, right? Which necessarily bounds some area. Through that area could or could not be flowing some current. What this says is that if that area bounded by this DL encloses some current, the magnetic field due to that current will be directly proportional to that current. The proportionality constant here is the magnetic permeability, mu naught. So I hope we see the similarities. If the symmetry allows it, this represents a much easier way to get the magnetic field of a current as opposed to the Biot-Savart law. So let's do one. Let's have a current, or a current carrying wire, and I'm going to draw this such that the current I is coming out of the page. Now, we're going to stick to the region for this example outside of the wire, mainly because I already know what that field is, right? I've actually solved for that using the Biot-Savart law, and I know what the answer is going to be, so I know I can tell if I'm going to be able to do it right. Well, this DL invites the construction of an Amperian loop. Remember, we had a Gaussian surface with Gauss's law. This DL invites the construction of an Amperian loop. And just like with Gaussian surfaces, I'm going to do my best to preserve any symmetry I might have. You might convince yourself you've got some cylindrical symmetry here. So I'm going to construct this loop with some radius r, which of course is user selectable. It needs to be user selectable because I need this to be a variable. I'm going to integrate around this. I'm going to integrate the dot product of b dot dl around this loop. So let's figure out what in the world dl is going to be. Well, let me just pick off one little section of that. Here is my dl. dl around a circle is always, at every point, is going to be tangent to that circle. So what this says is that I'm going to form the dot product b dot dl and integrate around this loop, the entirety of the loop. Now, in general, I could have a B field due to this wire. If I don't know the answer, the B field could be, whatever. It could be any magnitude, any direction. I can probably reason my way through saying that the magnitude of the B field is going to be constant, because I know if I've constructed this loop right, I'm always around this loop at a constant distance from the source. And I know that fields are source dependent. So I can probably just reason my way through to saying that the B field is going to be constant in magnitude around this loop. But if to take care of the dot product, I've got to look at the direction of the B field. And if I don't know that already, then what I can say though is in any coordinate system I'm going to attach here, I can decompose the B field at any point into vectors along my coordinate axes. This is, par for the course in mechanics. Here though, what are my coordinate axes? Again, the cylindrical symmetry is probably going to invite you to form a tangential axis and a radial or centripetal axis. So in general, at any point, the B field might have some tangential, or I'm going to call it a theta component, and it might have some sort of radial component, right? At every point, at this point, that would look like this. And of course, I'm kind of guessing at the directions, but here's BR and here's B theta. What I want to point out though is because of the path that I've chosen, where DL is always around the circle. Let's see what we can do with that. DL is my general placeholder. In this case, if I'm integrating around a circle, I'm going to rewrite this as the arc length, RD theta, times the directional component, which if I'm going around the circle is going to be theta hat. Okay? BR then, I can rewrite at every point as the BR vector at every point as the magnitude times the R hat vector. And everywhere I can write the B theta component as B theta times the theta hat direction, right? This is a standard procedure. I take this vector and I just write it as its magnitude times some unit vector. And in this cylindrical symmetry, around the direction around the circle, quote unquote, is the theta hat direction. The radial direction is going to be R hat. Now, look at this. This is a dot product. And mathematically, the dot product between any orthogonal vectors is always going to be 0. The dot product between any collinear vectors is just going to be the magnitudes of those vectors, the simple product of the magnitudes of those vectors. Well, what does that mean here? The path that I have chosen is all in the theta hat direction. The two components I have possibly are R hat and theta hat. But notice if I form the dot product between these two, right, I'm going to get 0. What I'm saying is if I'm really going to perform this integration, the way I would proceed is to break B into its components and do the integration twice. One for the B R hat dot R d theta theta hat. This is B dot DL. And then I would add to that plus the integral B theta theta hat dot R d theta theta hat. And that would equal, I enclosed. Fair enough. This would be generally how I would proceed if I need to integrate over two different components. But look at this. R hat dot theta hat everywhere is orthogonal because of my coordinate system. So everywhere this dot product gives me nothing, which means the only component I have contributing to the B field would be the theta hat component, the theta component, if you will. So that's just math, right? This just says that the dot product gives me 0, but the math and the physics have to go together here. So if Amperes law is correct, what this says is that the total field produced by this current is given by this expression. So if I find that any radial components are 0, if the physics is right, that means that there is no radial component, which means that all I get out of this integral is just the theta component. If we can hang on to that, let's actually do this integral. I don't have to call it B theta then. I can just call it B. So what I'm saying is this is actually equal to 0. And I'll just call this B theta hat. Make sure that's in frame. Yep. Fair enough. With that simplification, I've already reasoned that the B component along that circle is constant. I can pull it out of the integral. And Amperes law gets me then B times the integral, closed integral, over, R d theta, which is all I have left out of that dot product, gets me mu naught I enclosed. Okay, well, let's perform this integration. If I integrate r d theta around a circle from 0 to 2 pi, what do I get? Just the circumference of the circle, right? So I get b times 2 pi r is equal to mu naught I enclosed. I'm running out of room. Therefore, b is equal to mu naught. I've enclosed the entirety of the current in this case, mu naught I over 2 pi r. Well, that's good news because that's the answer. How do I know that's the answer? I've already done that with Biot-Savart. And I got mu naught I over 2 pi r. Of course, if I'm going to make this a vector, I've got to realize that this has a theta hat component. So this gives me the magnitude. I can add the vector nature just by inspection, noticing that I get only a component in the theta hat direction. So that's our first introduction into Amperes law.